changed the title because I do have transport actually in my talk as well, but at the time I was not quite sure what to expect actually. So I'm very happy to be here. I'm a chemist, but I've really enjoyed learning about turbulence and mixing and very different viewpoints on phenomena that I view often as chemical phenomena, but understanding the underlying physics and longer scale behavior has been really lovely. And so I do atomistic simulations of soft matter systems. And when I say soft matter, I mean both liquids as well as interfaces. And in the bulk liquids, these are often systems that have many dissolved components in them. So these could be concentrated electrolytes. These could be emulsions like we heard about earlier today. But obviously, kind of a key feature of them is that they have multiple length scale behaviors. So if you take, for example, the X-ray pair distribution function analysis of the solution structure, you can have organization up to the nanometer to sometimes tens of nanometer scales. And so we model and predict this type of longer length scale and multi-scale organization. We also look a lot at liquid interfaces, where we're looking at transport and reactivity at those interfaces. And in both sets of systems, whether we're talking about interfaces or the bulk, the characteristics of these systems is that there are multiple characteristic time scales of behavior as well as length scales of organization. And these influence the chemistry quite a great deal. And so this heterogeneity and multiple length and time scale characteristics comes about because we have very rugged underlying energy landscapes. And so when we do simulations, atomistic simulations, we're sampling different portions of the underlying potential energy or free energy landscape. And this means that we're sampling all of the index 0 and index 1 critical points, and sometimes higher order critical points are also relevant to some of the chemical transformations. And the real challenge is when you have these very rugged underlying energy landscapes, you have very broad ensembles of structure. And so this is just a simple kind of cartoon of a Gaussian-like distribution of different types of species we might see in one of these solutions where we have kind of organizational units, maybe monomeric building blocks that self-assemble into primary clusters and superclusters, and we've got this distribution of interconverting species. And they're interconverting based upon the barriers and relative locations of the minima on the underlying potential energy or free energy surface. And so the question becomes, when we do these atomistic simulations, how do we define the individual states of these very complex kind of architectures, and how do we relate them to the energy landscape? And oftentimes we want to relate this in a higher dimensional representation than chemists often like to use, where we use very simple two-dimensional or three-dimensional representations of energy landscapes. And so to do this, we actually develop and apply different types of mathematical analysis tools using graph theory, computational topology, and computational geometry. In the context of graph theory, we actually heard an application just the other day on some graph theory associated with transport phenomena. We use graph theory to identify patterns and correlations between particle-particle interactions. We do this to try and take the entire ensemble of all of the observed species in our simulations and decompose it so that we know the complete distribution of everything that's there. And we also use graph theory to identify collective behavior. And so this might mean, for example, new descriptors for mapping out free energy landscapes in biased molecular dynamics simulations. We use computational topology to encode variations in shape and structure in a very compact mathematical representation. And we can do this to analyze either point cloud information, like Cartesian coordinate distributions of chemical species, or if we use sublevel set persistent homology or superlevel set persistent homology, we can analyze manifolds and functions. In the context of computational geometry, we try to use geometry to identify complex structural features that occur at surfaces or with aggregates inside a solution. And so we're very collaborative, and we love analyzing complex data. And so we don't only, we do simulations, our simulations are always atomistic, but oftentimes we do analysis for other people. And so I just wanted to point this out because in case you guys find some interest in some of the mathematical tools we work on, we often analyze data and try to come up with new interpretations of data. And I have a really successful and long-standing collaboration with Jeff Morris from the City University of New York who does lubrication, discrete element method simulations of non-Newtonian fluids. And so, for example, we've done a lot of graph theoretical analysis of his simulation data to try and understand the origins of viscosity, phase transitions, and shear thickening and shear thinning fluids. And so if you ever have cool data that you think has really interesting shape and structure, please engage me. So returning back to kind of my overarching goals, where we want to first be able to take this complex simulation data and to define states of molecular assemblies or of surfaces and then relate them to energy landscapes, we often use graphs based upon intermolecular interactions where molecules become nodes, and if you have an interaction between them, then you have an edge. And we leverage the linear algebra associated with graphs significantly. There are many, many different types of matrix representations of graphs, all the way from just a simple adjacency matrix that just maps the connectivity patterns of nodes, all the way to the graph Laplacian. And we've developed quite a lot of different spectral graph theory descriptors of connectivity patterns of these graphs, and we've used them to identify lots of different trends and changes to chemical species and fluctuations and transitions in those species as well. For example, an older one, actually I guess some of this work dates back to nearly 20 years now, or 10 years now, is using some spectral graph theory descriptors to bias and map out free energy landscapes across multiple length scales in some of these complex solutions. So more recently, we've been really interested in developing multi-scale descriptions of chemical systems, and one of the ways in which we've been doing this is with hierarchical graph partitioning. And so imagine, this is just kind of a nice cartoon that I took and kind of showed some key characteristics of hierarchical or heterogeneity in graphs. Imagine you have a simple solution that's just made of monomeric units, and these monomeric units start to self-assemble into these small little disconnected subgraphs, and then they assemble more and more and more until you get a very, very heterogeneous network of self-assembled species. This could be a microemulsion, for example. We've been tinkering and kind of playing around with modularity optimization as a tool for getting multi-scale information of such heterogeneities, and basically this is using an optimization function called modularity I'll tell you what the math means rather than walk every single variable that they're defined up there. But basically what it's doing is it's maximizing and coming up with clusters or communities that are identified in the graph where the internal connectivity is maximized and the external connectivity between them is minimized. If you do this and you do something just like a simple Lennard-Jones fluid that has different particle strengths and particle sizes, you get self-assembly within this Lennard-Jones fluid, and modularity optimization is very efficient and very good at being able to identify these heterogeneities in a bulk liquid. We've actually been adapting it and recently adapted it with Ananth Kaliraman, who's a computer scientist, for temporal data. So we're really interested in transport phenomena, and so we wanted to be able to examine the surface heterogeneities at a liquid-liquid surface in time. And in time, if you have a network of intermolecular interactions, like on the thin film of a liquid-liquid surface, these communities or clusters are going to grow and contract. They might merge, they might split, some might be born, some might be dying. And so we need to be able to track these effectively in time. And so we defined temporal communities, which have some flexibility in the molecular nodes that participate in them over time. And this has very, very fast computational efficiency because we actually use the statistical observations of edge deletion and insertion so that we don't have to recompute hundreds of thousands or millions of snapshots in time. And so this algorithm needs to be rather large. And our graphs can be, also hundreds of thousands or millions of nodes and edges. And so doing this and using this approach to understand a very simple transport process across a liquid-liquid surface, here we have a metal ligand complex, so not a bare ion like we were looking at with the ion fingers the other day, but this is a metal ligand complex where you've had a surfactant that is absorbed, as Mark was talking about in solvent extraction yesterday, that is absorbed to the surface and complexed to metal. And when it complexes to this metal, it then forms this kind of little architecture or a fluctuation on the surface, and then it disengages. And the communities of water that participate basically in the bulk versus those that are participating in the interface versus those that are attached to this metal ligand complex, because there's some waters of solvation when they migrate across, all have different characteristic timescales of their fluctuations of this community. And we can identify bulk water as being a highly dynamic, very large community. The waters that are participating on the interface that are part of this metal-ligand complex solvation environment on the aqueous side are transitory and have much shorter lifetimes, or sorry, they're smaller, but have short lifetimes. And then when these waters migrate with the metal-ligand complex into the organic phase, they have very, very long-lived behavior. And so these different types of water species or hydrogen-bonded species have different characteristic timescales depending on what they're doing in the simulation. And we can identify them without knowing anything else about them at all, just based upon their characteristic timescales of behavior. So that tells you a little bit about maybe how you might think about heterogeneity in like a bulk system and how it's about individual molecules or these communities. What if we're interested in thinking about states or heterogeneities on surfaces? And so to do this, we have to have some kind of representation from going from an atomistic simulation to some kind of mesh representation of an interface. And to do this, we use Willard-Chandler surfaces, which are basically coarse-grained isodensity kind of surfaces of water density. And when we do this, we can then, and once we have this from our atomistic simulation, once we have the liquid interface represented in this way, we can map out, using sublevel set persistent homology, all of the minima and maxima and structure on this surface. And so basically the way sublevel set persistent homology works is if you have basically any discretized function or any actual continuous function, you introduce a filtration starting at the minimum of that function. This minimum is the first component on this function, and then as we increase whatever our filtration parameter is, which is the variable that the function is dependent upon, we might go over, we might, as we increase, let's say this is energy or height or something like this, we start off at the lowest energy component or the lowest component, then another component emerges from a second minimum. When we increase our filtration and overcome the barrier, then those two components merge. So then we only have one component. As we increase our filtration even further, then we have another component. These two components merge when we overcome this barrier. And the representation of this encoding of all of the components when they're born in the filtration space and when they merge or die in the filtration space can be encoded in this very nice barcode representation. And this barcode tells you basically everything about the topology of this surface. It does not tell you about gradients on the surface, but it does tell you about all the locations in the filtration space of all the minima and maxima. And you can also go to very high dimensions with this representation. It does not have to be low dimensions. So we've used sublevel set persistent homology to analyze lots of different types of liquid-liquid interfaces, and this is kind of a growing capability. One of the first things we did was we were looking at the heterogeneity on a liquid-liquid surface based upon adsorbates. Because the thermal fluctuations and self-assembly of some of these surfactants on the surface actually lead to a lot of heterogeneity at the liquid interface. And so we created time-dependent density images, basically, where we projected the density of the surfactant onto a plane and converted that into a bitmap representation, and then encoded that bitmap representation as this heterogeneity kind of barcode, if you will, of the adsorbates on the surface. And so one of the things you can do, and I'll just tell you, I missed one little thing. So here's the projection basically of adsorbate density onto a plane to create the bitmaps. Here our filtration is the density of the surfactant. And so you'll see that we've got 1, 2, 3 bars. These are called these Betty numbers or beta 0 numbers are the original number of components. And when the components merge and create a whole, you get a higher dimensional piece of information, which is called the Betty 1. So we're keeping track in this type of representation or barcode representation for persistent homology. We're keeping track of the number of components, which are the Betty zeros, and the number of holes or cycles that emerge as a consequence of this. And so if you look at, for example, the distribution of these Betty 0 components and the Betty 1 holes, you can very clearly distinguish between very heterogeneous versus much more homogeneous distributions of adsorbates on surfaces, and we can do this over hundreds of thousands and millions of surfaces from our simulation to get really good statistics of how they're differentiated from one another. And we can develop descriptors that then are correlated and actually have very nice tendencies towards macroscopic information of these interfaces. And so, for example, we can look at what's called the persistent entropy, which measures the variations in the lifetimes of these bars in the barcode representation. And we developed what's called a non-ideality index, which is where if a surfactant adsorbs to a surface and they don't interact, then the number of components basically is the number of adsorbed species. But if they start to interact, then the number of components decreases relative to that. And so we can identify and say that, okay, the number of cycles, or the number of, if the components are smaller than what they should be, this means that they're interacting, so it's non-ideal. And we can take these descriptors based upon these barcode representations, and they track very linearly with things like surface tension and other properties of the interface. And so these descriptors are capturing some of the fundamental features of the distributions of these adsorbates that are related to the surface tension. We can also track these descriptors in time and observe their fluctuations in time. And so in this non-ideality index that we developed, an I value of 1 is ideal, and an I value much less than 1 is non-ideal. And so if we have, for example, a non-transporting interface where we have a pretty flat surface where all the adsorbates are relatively homogeneously distributed but nothing's really happening, then the non-ideality index is kind of in the 0.7 to 0.8 region. But if you have a transporting interface where things are moving on and off, and as a consequence of the transport actually occurring, the surfactants are collecting together, then we have a very low non-ideality index that is very characteristic of this transporting interface, and you get much larger amounts of fluctuations in this descriptor space. Another thing that we have done is to look at the geometry of interfaces beyond things like surface curvature and things like this. We're very well aware of the literature associated with surface curvature, and it's been very useful. But in a lot of these cases, because these kind of reactive surface assemblies associated with surfactants where chemistry is going on have very odd shapes. A lot of the typical surface descriptors, geometric descriptors like curvature, are not really capturing all the anisotropy and deviation in these surfaces. And so we started to adopt some image denoising technology where basically the idea is that there is an ideal flat surface underneath this very, very rough reactive surface. And what we want to do is we want to systematically pull off and identify these structures that are on top of this ideal flat plane, and analyze their behavior, analyze their reactivity and their shape and their evolution in time. And so this is very similar to if you pull out, your favorite image maybe from your grandmother's closet, and you see that there's all of this noise and pixelation on the surface. Those are like rough patches on top of an ideal flat surface, and so we're pulling those off. And so the approach that we use is called geometric measure theory, and this was a collaboration with a very good friend of mine, Bala Krishnamurthy, who's a mathematician. But the idea here is this is just an optimization problem where we're going to pull off some set amount of area in 2D space or volume in 3D space, and we're going to try, and the optimization is finding the ideal curved surface underneath, the smooth surface underneath of it. And so we can control the amount of area or volume that we take off, depending upon the dimensionality that we're in, by tuning this lambda parameter. And so if we decrease lambda, we take off more and more volume on a surface. This is a meshed image of one of our real surfaces. And so at large lambda values, we only take off small volumes. We start decreasing lambda, we take more and more volumes, and we're keeping track of the components that are pulled off of the surface. And the components, as we pull off more and more volume, they merge. So, originally right here at very large lambda values, we had 3 components. Then these 3 components merge into a single component, and this component grows and grows. And through this approach, we can then identify these very interesting structures that emerge as a consequence of surfactant self-assembly on the interface. And what's really nice is we can actually identify the exact same surface structures using modularity optimization, that temporal modularity optimization that I showed you. And so we've got self-consistency in this identification of these surface architectures, which is really nice. And so we've been able to use this approach to classify different transport mechanisms for oil-water interfaces in things like solvent extraction. And so we've kind of been able to bin them into two groups. The first group is when you have transport processes that are based upon the fluctuations in this instantaneous surface. And this includes the water fingers that were talked about the other day, as well as larger architectures, which we call protrusions, that derive from surfactant self-assembly. And so this we call primary structure transport because it's based upon the primary instantaneous surface fluctuations only. But then there's also types of interfaces that you can have, depending upon the surfactant, where you get what I call secondary structural organization. And so octanol is a really good example of this. So here's a picture of octanol. At the octanol water interface, octanol actually kind of behaves like a lipid and will organize into something that looks almost like a lipid bilayer, but not quite. It's very, very defect laden. And so if we look just at a heat map of the OH head group density at the instantaneous surface, you can see it's pretty evenly distributed. Those hydroxyls of that octanol are pretty well distributed, the ones that are directly in contact with water. But if you look at a layer away, where you've got now the bilayer part of the membrane, of the octanol membrane, a layer away, you can see that there are these patches. And we call these patches bilayer islands. And it turns out we can control the formation of these bilayer islands based upon the concentration of octanol. And so at very low octanol concentrations, we have this very, very flat, there's not very much absorbed to the oil-water interface. As we increase our octanol content, we start to get more structures. And then by the time we get to 80% octanol, you have this kind of bilayer-like structure that forms. And if you start monitoring and use these tools to monitor the dynamics of these octanols, this was done with a graph theoretical framework, we can actually see that they have a very, very different mechanism for transport relative to the primary transport where we have water fingers or protrusions. And so this is just a time-stamped kind of set of images, but here we have some octanol, and this is the Willard-Chandler surface. These are octanols that are facing and directly hydrogen bonding with water. And there's a small group of them that are a little bit more tightly hydrogen bonding, and you have a binding event where water binds these octanols, and then the octanols flip like a hinge into this second layer, and then they release. So there's the flipping event, and then they release the water, and then you flip back down. And so just a kind of a better cartoon image is here's our octanols facing the aqueous phase. We have a binding event, they flip, and then they release. And so we call this a molecular hinge mechanism for the transport process that is involving this secondary structural features away from the instantaneous surface. And if you analyze, I don't know, we had like hundreds of thousands of these events, we were able to identify all water transport processes, and something like 83% were transported by this hinge mechanism. And we could very, very clearly delineate that transport process relative to diffusion or stochastic flipping of individual octanols that might carry a water with them. The beautiful thing about this hinge mechanism is it follows a very nice double harmonic well, simple potential energy function. And so you can do Langevin dynamics and actually totally capture the transport process with this very simple model using the barriers that we identified from our simulations, our atomistic simulations. And so this secondary, this alternative transport process that we've been able to identify using some of these tools, we call secondary transport. And this would also include other things like maybe micellular budding or very large kind of structures that result from organization in the interfacial region and not directly with the instantaneous surface itself. So this kind of tells you a little bit about ways that we think about defining states and how when we sample this configurational space. And so I'm going to end by talking about how we can relate this to the energy landscape, because this is, I think, really kind of the most powerful forward-thinking kind of concept here. And in particular, we want to be thinking about these higher dimensional representations of the energy landscape for these types of processes. And so we need to be able to have a compact representation that captures all the topology. And the typical technique that's used in like protein folding and things like this are what are called merge trees or disconnectivity graphs. And these disconnectivity graphs just map basically all of the index 0, all the minimums in a tree-like formalism. Now, the problem with disconnectivity graphs is that you can have two very different energy landscapes that have exactly the same disconnectivity graph, because the disconnectivity graph only knows about this low dimensional information in the topology. And so if you've got higher order saddle points or something like this, then you miss those. And so we're going to level set persistent homology, but this time instead of doing filtrations on density on a surface, we're now doing this on an energy landscape. And so this allows us to capture a lot more information about the topology of the energy landscape. The bar lengths, so the barrier heights, the number of bars, the number of barriers. We've got all the indices of all the critical points, and I'm going to show you some of these that are very, very high dimensional in a minute here. And this also allows us to create and think things like distance metrics for how we quantify how different two energy landscapes are, for example. And we can start thinking about patterns that might emerge in an energy landscape that dictate the fluctuations that we observe, both across interfaces and with interconversions in the bulk. And so I'm just going to go through a really simple example, and then I'm going to show you how we want to apply this in the future, because this is pretty recent work that we've been doing in collaboration with Henry Adams, who's a mathematician at the University of Florida. But imagine you just have a single molecule, and this single molecule has just a barrier for rotation. It can rotate around this bond right here. Here is the simple potential energy landscape for the rotation associated with this bond. It's got a global minimum, which is this bar here. This is butane. And then these two slightly higher minima start here. And so the relative energy differences between the start points of these are the differences in energy between the two minima. And then there's our barriers, which are when these bars die because these components merge. Now imagine we make this molecule bigger, okay? And so I've gone from butane to now a pentane. I've added a carbon atom. And for every carbon atom that I grow or add to this system, I'm adding 1 degree of freedom associated with this rotation. And so I go from a potential energy like this that has 6 critical points. That's basically it's a torus, a one-dimensional torus or a circle in topological space, to this more small complex here, which is a little bit more complicated. And I can do this over and over and over again. And what happens is that these the resulting potential energy landscape that I have for this molecule as it grows is a series of nested functions if those terms can be added together. So if it's an additive potential energy landscape, then I can do this. And what I can do then is I can mathematically prove, I can use the fact that this potential energy landscape is a series of nested functions to then mathematically prove the number of bars in any dimension of space that I want, and their birth and their death times. And so we did this a few years ago, first in JCP, and then we extended it to more complex molecules that are these branched alkanes. And basically, again, we were just able to show that basically the sublevel set filtration is kind of this tensor product based upon what we call now building block functions. We can now take individual building blocks of these the sub parts of a molecule and build up the potential energy landscape from those. Then we can prove what the final potential energy landscape is. And so here's some building block units of small molecules. Here's their potential energy functions of those building blocks. Here's their sublevel set persistent barcodes. And basically there's a finite number of ways that you can add all of these together to yield a total potential energy landscape. And so basically it's a combinatorial problem, and I'm not going to go through that because I'm running out of time. But I do want to show you how complicated these potential energy landscapes are and how powerful this approach is. And so here's this molecule here, which is this branched molecule. And if you use these building blocks, like I said, we can predict it's only a 7-dimensional landscape, so it's not that big, but look at the number of critical points. There's 840,000 total critical points on this 7-dimensional surface with 32 minima, a whole bunch of minima, all under 1 kcal per mole, and it's because this molecule is really floppy. It can move around a lot. And 1,200 index 0 critical points before you hit 2.75 kcals per mole. So this is a pretty complicated potential energy landscape that comes from a really small molecule. But we want to use these tools. And we can also predict what happens when we now have chemical reactions. So if we have a reaction where we have a bond that forms maybe in our solution, we can see how the barcode and predict how the barcode will change that molecule. And so this just came out, I think I forgot the reference, it came out in JCP earlier this year, so it's there. The cool thing about this is this provides a consistent mathematical framework, actually, for thinking about structures that are in our liquids or across our surfaces, because we were using sublevel set persistent homology to encode those. We can also encode the energy landscape using the exact same mathematical language. And I think there's a lot of power in that. And so what we're trying to do right now, going from this simple molecular example to much more complicated examples where we're sampling free energy landscapes, we now want to do the same thing where we're encoding the energy landscape for things like transport and interconversion and microemulsions and things like this with the underlying structures that they correspond to. And so with that, and that's what we want to do for these primary and secondary transport processes. And so with that, just acknowledge the Department of Energy. Here's my most recent group photo for moving to the University of Utah. This was largely funded by the Department of Energy Separations Program as well as NSF. And so I'm happy to take any questions. Thank you.
Thank you very much for the interesting talk. Any questions or comments? Very interesting.
Oh, thank you.
So I'm interested in the early stages. Given the graph representation of atomic connectivity, and like a graph Laplacian, and you mentioned coarse graining.
Yes.
What is the process of the coarse graining, and what is the end product?
Yeah, so if you use modularity optimization, you can do it in multiple passes. And so what happens is you go from a molecular level graph to then to a graph that is made of communities where those molecules have assembled together. Those can become nodes, and if those communities are interacting, then they will have edges between them. So this could be used, for example, I've got a student who's using this to study microemulsions. So we have a graph of all the molecules that are in the micelles that are in the microemulsion. Then we use modularity optimization and coarse grain that graph to then create a micelle-micelle graph, for example. And then that micelle-micelle graph can be related to things like small angle X-ray scattering of the solution structure. Yeah.
What is the calculation of coarse graining?
What is the calculation of coarse graining? What do you mean?
Coarse graining means some average of ensembles or.
So we do not. So when we coarse grain, we are coarse graining the graph, right? We're taking the connectivity patterns in the graph and we're making that connectivity pattern a new node. We are not doing so we get a new ensemble of that graph that does contain the information about the more highly resolved graph. But then we study what we would call that coarse-grained graph. We don't necessarily do, we don't take that graph and then create some kind of continuum approximation or anything like that. We don't do anything like that with it.
Yeah. Later, I'll ask you.
Yeah.
Thank you.
Okay, short questions. Time is already over.
So with your ligand computations or whatever, what's the largest molecular weight that you can work on your computers that you'd sit there and say, we can do this, or this is too large of a complex assembly?
Sure. So our simulations can be quite large. Most of our, because, so we don't think about it in terms of molecular weights because we are dealing with things that are like in liquids, right? So maybe a total number of atoms that are in the, 400,000, 500,000 atoms in a simulation, something like that. Yeah. Yeah.
Okay. So time is actually up. So thank you very much. Okay.